Hi everyone. In this video, I'm going to consider two kinds of products between vectors that originated in the study of mechanics and electricity and magnetism. So the first product is the dot product. The dot product is also known as inner product or scalar product. Let's say that we have two vectors, vector A and vector B. The dot product of these two vectors or any two vectors is scalar and is defined as, so as you can see in the dot product, we will multiply the first components of the two vectors and then add it to the multiplication of the second components of these two vectors. And the third term will be the multiplication of the third component of these two vectors. And here the result will be scalar or a single number. There is also an alternative form of the dot product, which is the magnitude of A times the magnitude of B times cosine of the angle between these two vectors. So if this is vector A and this is vector B, then this will be the angle theta. So here, as you can see, if the angle theta between these two vectors is equal to 90 degrees, then cosine of theta or cosine of 90 degrees will be equal to 0. So now we can conclude that two vectors will be orthogonal to each other if and only if the dot product of that two vector is equal to 0. So we can write a criterion for orthogonal vectors, which says two non-zero vectors A and B are orthogonal if and only if the dot product of these two vectors is equal to 0. So as you know, orthogonality means that two vectors have the angle of 90 degrees. So here, if we have vector A and also a vector B, and the angle between them is 90 degrees, which means that the cosine of 90 will be equal to 0. So the dot product will be equal to 0. So using the dot product, we can also find the angle between two vectors. So the angle between two vectors will be equal to, so here from the dot product, we have cosine of theta here. So we can say that cosine of theta is equal to A dot B divided by the magnitude of A times the magnitude of B, which we wrote it here. The dot product will work in both two spaces and three spaces, or in two-dimensional and three-dimensional. In here we showed the 3D case, but if the vectors are in 2D, then here vector A will be only A1, A2, and vector B will be only B1, B2. Then the dot product of these two vectors will be A1, B1 plus B, A2, B2. However, cross product only works in 3D. So the cross product is only defined for vectors in 3 space and results in another vector in 3 space. So again, let's say that we have a vector A and also a vector B. Then the cross product will be defined as the determinant of this matrix, which will be equal to I times the determinant of this submatrix. And since here I is the array of first row and the first column, then this summation is equal to 2, which is an even number. So here this will be positive. Then we will have the second term, which is the multiplication of j and the determinant of this submatrix A1, A3, B1, B3. And in here, since J is in the first row and the second column, and this summation is equal to 3, which is an odd number, then the sign here is negative. And the third term is the multiplication of K and the determinant of this matrix, submatrix. And here K is in the first row and third column, and this summation is equal to 4, which is an even number. So here we will have a positive sign. So this is the definition of the cross product, which is only defined in 3D. The magnitude of this cross product is defined as the magnitude of vector A times the magnitude of vector B times the sine of the angle between these two vectors. So similar to dot product, here we can form a new theorem, which is the criterion for parallel vectors, which says two non-zero vectors A and B are parallel if and only if the cross product of these two vectors is equal to zero. We know that two vectors will be parallel if the angle between these two vectors is equal to zero. And if theta is equal to zero, then its sine will be also equal to zero, which means that two vectors are parallel if and only if the cross product is equal to zero. But what are the applications of dot products and cross products? So let's say that we want to know what is the component of a vector on another vector. So let's say that this is vector B and we want to find the component of vector A on B, and the angle between these two vectors is theta. So the component of A on B is here, where this angle is 90 degrees. The magnitude of vector A times cosine of the angle between these two vectors. In other words, to find the component of vector A on an arbitrary vector B, we can dot A with a unit vector in the direction of B. So here we have vector A, and we can find a unit vector in the direction of B using this fraction. So the component of vector A on B is a scalar that essentially measures how much of A is in the B direction. So this component gives us the measure or the magnitude of this vector here. But what if we want to find this vector itself? Then we need the projection. So the component of vector A on B is this magnitude, but the projection of A on B is this vector, which is defined as projection of vector A on vector B is equal to the magnitude of the vector, which is the component of A on B, and now we need a direction for this magnitude. And this direction should be a unit vector in the direction of vector B. B will be equal to the vector B divided by its magnitude. So this will be equal to this vector, which here we will have a scalar or number, and here we will have the vector. But what is the physical interpretation of the dot product? Let's say that we have a surface and a body on that surface. When a constant force of magnitude F moves an object a distance d in the same direction of the force, and this distance will be d, then the work done is simply equals the force times the distance. But what if this force is not in the same direction as the displacement? So let's say that now we have a force in a different direction, and now this force forms an angle theta with the direction of the displacement. So now if we exert this force on the body, then the object will move a distance again. And again, the displacement now is d. But this time, the force is in a different direction than the displacement. Here is the displacement direction, and here is the force direction. So in this time, work will be equal to the dot product of the force and the displacement vectors, which we had it in high school to be equal to f the cosine of theta. So this comes from the dot product. So far, I've talked about the application of the dot product, and now I'm gonna talk about the application of the cross product. So let's say that the vectors A, B, and C do not lie in the same plane, and they form a parallel pipe. So let's say here, these are the three vectors that we have. So the volume of this parallel pipe, which is formed with edges A, B, and C will be equal to the area of the base times its height, where the area of the base is highlighted in red, and is equal to the cross product of vectors b and c, and is equal to the magnitude of the cross products of vectors b and c. And using the right hand rule, we know that the cross product of vectors b and c will be in this direction. And now we need to find the height of this parallel pipe. So as you can see, the height of this parallel pipe will be equal to this distance. So we need to find this distance. So as we know, this distance will be equal to the component of vector A on the cross product of vector B and C. So here, this distance will be equal to component of vector A on vector B cross C. So the height is equal to, and we know that this component is equal to this. And the whole thing will be equal to our assumption to find the volume of a parallel pipe was that the vectors A, B, and C do not lie in the same plane. And also we know that a parallel pipe will have a non-zero value for its volume. So now we can conclude that if this volume is equal to zero, that means that the three vectors A, B, and C do lie in the same plane, or we can say that those three vectors are coplanar vectors. So now we can conclude that this is equal to zero if and only if A, B, and C are coplanar.